So this is the number that we got running this program sequentially. No parallelism. It took 1.25 seconds. Now, there are many ways of parallelizing this program, and one of them was to take this long array of list of puzzles and just chop it into two and run two halves in parallel. Okay? And that gives you some parallelism, but it so happens that the second list has harder puzzles than the first half. So you get some parallelism until you run out of the first half, and then the second half continues on a single processor. So that's kind of not very good. The opposite of this is what I'm going to show you now, is splitting it into tiny things, okay? Because creating sparks is cheap. It's just putting a pointer in this spark queue, right? It does a little bit of synchronization, but it's relatively cheap. So creating sparks is pretty cheap. So we can create like 1,000 sparks, and it's fine, right? And the processors will just compete and steal these sparks, and more or less will distribute the work equally between processors, more or less, right? So the more sparks you have, the more equally you can distribute them. And of course, the more sparks you have, the smaller these sparks are. So you, at some point, you hit this granularity problem when your sparks just contain a few instructions, and the overhead of sparking actually overtakes any benefit. But in this case, the spark would be the solution of a single puzzle. It's big enough, right? It's not too small. So before we do this, we have to introduce a new primitive, because what we are going to do is go through a list and apply and spark a calculation for every element of the list. So we have a function that we want to apply to every element of the list. So it's sort of like map, right? But we want to do it in parallel. So this function is called parmap. It maps a function, but it sparks the application of this function for each element of the array, of the list. So parmap has a signature that's very similar to map, right? So it will take a function from A to B, right? That's the function that we want to apply, and it will take an array of A's, right? And normally you would say that it produces an array of B's, right? Except that we are sparking this stuff, and sparking produces the eval, encapsulates the result in eval. So it will produce an eval of a list of B. Okay? So it's very, very similar to map. So how do we implement this thing? Well, one of the arguments is a list. So how do you implement functions on lists? You pattern match to empty list and head and tail. So what should parmap do? So there's some function f, right? And empty list. What should it do to an empty list? What should it do? Yeah, it normally will return an empty list, right? But we need something of the type par. So we'll just say return. Return empty list. And we'll just lift this empty list to the eval moment. Good. Okay. Now another pattern, parmap. Okay. And here I could put wild card. because I'm not using this function. But here I am. Here I am. And I'm pattern matching on, what should we call it? Aids. Okay? Head, tail. And we are doing some monadic calculations, so we'll start with do. Right? And inside this do, well, we have to do two things. Spark F acting on A, on the head. Okay? So we'll just call R par on FA. And the result of this is, let's say, some B, right? This F turns A's into B's. Okay? This is really a value, not a type, right? We just name these values. Now we have to apply F to the tail. Well, how do we apply it to the tail? Well, recursively, of course. We'll just apply parmap to the tail. So we'll call these B's. And we'll apply parmap F to A's. Right? So we call ourselves recursive. And of course, what parmap will do here, it will spark the head of the tail and then apply itself to the tail of the tail. Right? So it will go recursively spark every element eventually. So all the elements of this list will be sparked. And finally, we have to reconstruct this list from B's, right? So we'll say return a list that's B column B's. So we are recreating this list from the head and tail, right? And we apply return to it because we want this to be in the eval mode. Potentially seeking even more parallelism at some later point. Because as long as when we are working in the par monad, we can just like keep sparking more stuff, you know, without actually executing. And the more we do this, the more parallelism we get. In this case, we are done more or less here. So the change to this implementation is really trivial. The only change, I'll put it in red. So you'll see how easy it is to parallelize these things in Haskell. Instead of map, yeah, I'll put par map. And that's it. No? Is that great? Now, I skipped the first application of parallelism when we divided the list into two halves. And there was some tricky part in there where we actually had to force the evaluation of the elements of the list because otherwise it would be evaluated to head normal form, right? Weak head normal form. And evaluating a list to weak head normal form means just evaluating the first, the first constructor, which is combining head with tail. And this is no work, right? Nothing. Just there's very little combining head and tail, right? We don't have to evaluate the head. We don't have to evaluate the tail. We are done. Okay. So we had to like force deep evaluation. Here we actually don't even have to do that because evaluating a solution to the puzzle to head normal form, to weak head normal form. Remember what a solution is? It's a maybe, right? So in order to evaluate it, we have to evaluate this maybe. So evaluating maybe to head normal form means we have to find out which constructor was used to create this maybe. Was it nothing, or was it just? Right? Now, in order to find out that, we have to solve the puzzle. There's no way. Right? So we don't have to force anything because shallow evaluation is fine in this case. It forces the solution of the puzzle anyway. Okay? So now, Richard, show us how this works.
Script. See what happens. So, if you care, the command lines are there. It's the same as before, the only thing is we're using a different source file, sudoku3.h. It's collecting the stats in the same way, and the line that we care about is this one here. Specifically the time of the
Yeah? What's the time?
0.608 seconds. So
Factor of 2.
0.61 rounded to decimal places. 0.61.
Are you sure you ran the Spark one? Oh, you have only 2 processors.
This is not a terribly beefy machine, I'm afraid.
Oh, you have only 2 processors. Okay.
Let me try bumping up
So we
NT.
cannot really speed it up any more than 2 times. Right. Okay.
Yeah, we're
Okay. Can you show us ThreadScope?
Yeah, ThreadScope will generate an event log. I can then load that.
Okay, so there is this tool, ThreadScope, that actually visualizes what's happening, what's when it's running parallel, when it's not.
Also open the log.
Okay. So I'm gonna zoom on this. Okay.
I actually ran this with N4, so.
Oh, you ran on 4 processors.
Yeah.
So it should be 4 times faster, right? Because it is using the 4 processors.
Looks
What
like
happened, Richard?
What did you do?
It's using 3 processors. It looks like. No.
4. It's using 4 processors. So the bottom, the 4 bottom ones are the activity of a single process of every processor, 1, 2, 3, and 4, and the top is just the overall. So one thing that you can see here, and it's very interesting, is in the beginning of the program, only 1 processor is working, right?
Yes.
But other than that, and at the end of the program too. But other than that, and the orange lines show garbage collection, right? So there is a lot of garbage collection happening in the beginning, and this is when we are reading this big file. So what Richard was saying that I have to put run eval here, run eval before parmap. Okay, run eval over, because parmap will return an eval of B, right? Eval of a list of B. And what we want is we want to extract this list finally. So we have to run eval in front of parmap to get the final result.
Yeah, I think we're going to do this demo again for an audience. I need to somehow have a much beefier machine with like 32 cores.
Yeah. Okay, so you've seen that the beginning of this program was actually not parallelized. It was the beginning when it was reading the file. So it is actually a little parallelized because the reading of the file is lazy. So it just leads 1 buffer from the file and then starts splitting it into lines, right? So as soon as it reads the first buffer, the splitting of lines starts happening, and then goes back to reading the next part of the file and splitting of lines. And as soon as the lines are split, the rest of the algorithm can actually start sparking stuff. And this is when the parallel work starts. But in general, every program that has some parallelism will have parts that are parallelizable and other parts that are not. And this is illustrated in this famous Amdahl's law. Okay, let me just quickly show you what Amdahl's law is. The derivation of Amdahl's law is really, really simple. So let's assume that there is a fraction of the program that's parallelizable. So let's call this fraction of a program P. Let me use some other color. So P is the fraction of the program that can be parallelized. 1 minus P is the fraction that cannot be parallelized. Okay? So the total time when it's run sequentially is just the sum of these two, and it's 1. Right? Because we normalized everything to 1. So this is how long the program runs when it's run sequentially. No parallelism. The parallel part actually runs sequentially. Now if we have n processors, okay, then we get a speed up, right? We will have to still execute 1 minus P, because that's the part that cannot be parallelized. So this part will still run sequentially. But the parallel part will be run faster. It will be P divided by N, where the number of processors, N is the number of processors, right? It's there's this 1 minus P. Right? So the speed up is dividing this by this. It will be a number that's greater than
1 minus P.
1. So the speed up is 1 divided with 1 minus P plus P over N. Okay? This is the Amdahl's law. But what's interesting is, well, suppose we have lots and lots of processors. How much can we speed up this program? Well, let's say n goes to infinity. Right? If n goes to infinity, this term here goes to 0. Right? So we can just cross this term and say the speed up will at infinity of processors will still be only this, right? 1 divided by 1. So there is a limit to speed up. You know, it will go up and up, right? But then it will slow down and reach a certain thing. Constant. So this is like a big problem in parallelism.
So
That-
is there
You can only gain speed up on the part that's parallelizable.
So is it possible to define the parallelizable or to compute what's parallelizable and what's not?
Well, when you are writing your algorithm, right, and you parallelize it, you say, I'm parallelizing this part. I put my par map here, or do these things in parallel, and so on. So as long as you can satisfy all n processors, you have sparks enough for the n processors, this part of the program will run as P over n, right?
Now, there are some assumptions being made here, right? Like, there are no costs associated with dividing the work up.
Right. So it's a simplified model.
Yeah.
Yes.
I just wanted to give you an update. I figured out that n minus 4 is optimal, and that gives you 0.51 is the elapsed time. 0.51.
0.51.
Yeah, that's with n equals
Okay, so
4.
that's better.
I figured out the option for GAT to tell it to figure out the number of calls itself. Yeah, dash n by itself, so it will figure out the optimal number of calls for you. But it tells you how many it figured out. So for
So it's not a bad speed up.
I think it's 2 cores and they're hyper-threaded. So
And it was so easy to do.
Why, you chose a problem that was easy to do.
Well, and that's always true with demos of parallel programming. This is nothing about Haskell. What's special about Haskell is that it's easier to implement and virtually no debugging is needed. Okay? That's the strength of Haskell. Now, parallelism is a tricky business. Right? And there are some algorithms that are parallelizable, and there are others that are not. And then we hit the Amdahl slot. That's just life.
To see how
That's
much
just
time
life.
it took to read the file versus how much time it took to do the job.
Okay.
we can probably zoom in on the ThreadScope to find out the sequential part we can do something. So yeah, that was a trivially parallel algorithm there.
Yeah, what do you expect? It's a demo.
Cool.
But the idea is that, suppose you are processing lots and lots of data. So you have some serial part of your program, and then you have the parallel program. But the more data you are processing, the longer this parallel part will be, right? So it actually lets you process more and more and more data, and you get this speed up because you're increasing the amount of data that you can process. Yes?
So when you're doing like stuff with I/O, I worked on something where I wanted to parallelize it. Like, how do you approach it? How to find the best balance of like how to chunk it up and how many cores to use and all that? Is it just like measure, measure, measure? Or?
Measure, measure, measure. Yeah, it's always true about parallelism.
What you just did, there were no measurements. You just wait for a processor to be free.
Yeah, yeah.
Or richer measure.
I think when they came up with this demo, they did some measurements.
Richard didn't do anything except say use whatever cursor goes.
Well, in the last case, but I could have, I tried many different values of n, and I could have, plotted a chart, a graph of elapsed time versus number of cores, and figured out the optimal that way. And I figured out actually by myself that it was 4, but then I thought maybe there's a way that the Haskell runtime system will figure that out for
It
me.
doesn't always have to be that case.
That's true as well.
Okay, this is something that they actually mention in their paper, is that if you have 4 processors, they left one free for the operating system to run. Because otherwise the results were very inconsistent, because the operating system would just like get in the middle of the, so for wall clock timing, very inconsistent. But if you leave one processor free, then the operating system can use it, and you can obtain almost 3 times speed up, which is what we got.
And this is also very CPU bound, but if you have an I/O bound problem, it's very different.
Oh yeah, yeah. Unless you can do I/O in parallel, reading multiple files.
Yeah, that's what I'm saying, but then those settings might be,
Yeah.
you could use more threads than just the number of processors you have.
Okay, let me continue. So, we talked about this difference between weak head normal form and deep evaluation, right? So, now is a good time to actually talk about how do you do deep evaluation. So, so Simon introduces here a function called force. That forces deep evaluation. So it's really sort of like an identity function. It takes something to be evaluated and returns the same thing, but it's already evaluated. So this is a thumb for A, really, supposedly, and this is the full evaluation of it. So it is, semantically, it's identity function. Right? Now, this will not work for every data type. Data type A has to be of a special class that can be deeply evaluated. Right? And this class is called NF data, normal form data, A, double arrow. So assuming that A belongs to the class NF data that can be deeply evaluated, then force has this really identity, right? We use it for side effects. So what is this class NF data? Class NF data A, where? Now we started with these classes that actually contain type constructors, which are like higher order classes. This is just a regular class that's been used in Haskell for a long time. It's just a type. So a type, particular type, belongs to this class. Unlike monad or functor that were type constructors belonging to a class, here is just a type. And it has just one function, RNF, reduced to normal form. And this function takes the A and returns a unit. Thus, it's just for side effects, right? The side effect of this function is the evaluation. So it can just easily return a unit, because we are not interested in what it doesn't calculate anything. It just calculates A, makes A turn from a func into a value. And that's something that's invisible from the semantics point of view. It's totally invisible. And in the definition of a class, it's always possible to write a default implementation. It's like something that will work for like primitive data types. So for primitive data types, RNF is simply defined as a seek with unit. So we've seen this stuff before, right? That just forces the evaluation of A. It forces the evaluation of A to weak-head normal form, right? But that's good enough for all basic data types, like integer, Boolean, you know. So that's good enough. Now, if you want to make your own data structure into NF data, then you have to provide your own implementation of RNF. And here we have an example. Okay, well, I mean, let's say we have this tree that I showed you before, right? So is tree and NF data? Yeah, for a tree we can say instance NF data of tree of A. Okay. But that's kind of too weak, because like if you want to deeply evaluate a tree, you also have to deeply evaluate A's, right? That's what deep evaluation means. So how can you deeply evaluate A? You can only do this if A itself is NF data, right? So in fact, you put this here as a precondition that NF data A. So instance NF data A. Do I put parentheses? No. now we have to define our RNF on a tree. I remember tree had two constructors. One was empty tree, so defining an RNF for empty, well, it's kind of trivial, right? I mean, RNF is supposed to return unit, so we'll just return unit, right? So on empty tree, RNF does nothing. However, if you apply RNF to a called a node left, then there's some A, and then there's the right subtree. Left branch, value, right branch. Okay, how can we define this? Well, obviously recursively. So we'll apply RNF to left, we'll apply RNF to right, and we'll just evaluate A, right? So RNF left, right? Acting on left, then we sequence it. Oh, I didn't say how I do this. How do I do this? I put this stuff in backticks. Okay, if you take a function and put it in backticks, you can use it as an infix. So it's sometimes very nice to just say, okay, do this and then do something else. So seek used as an infix operator, which is kind of spell things nicely. Seek takes two arguments. We want one argument to be on the left. So we'll do RNF on A, seek again, and we'll do RNF on right. Right? I mean, we are defining RNF on trees. So this is RNF on tree, and this is RNF on tree, but it's a smaller tree. So the recursion will work nicely. And we can apply RNF to A because we assume that A is NF data.
Oh, so that's just a default implementation from the instance?
That's the implementation of our. It overrides the default. So if you provide your own implementation, then default is overridden, right? So
okay,
it's
but in this case,
like your base class has, your interface has a, well, no, in Java you cannot have the functions, methods defined in the interface, right?
And in Scala, there's traits in Scala allowing you to have a...
But assuming you have what you have on the board, this would refer to the RNF default implementation.
Well, it would refer, it's a different RNF for the RNF.
Well, if A were, let's say, integer, okay, then for A we would use the default implementation. But it doesn't have to. It could be another tree or list or something. So we would use RNF for list, which is separately defined in the instance for list. And most basic data structures are actually included in the file that defines NF data. So it has implementations for lists, pairs, and so on. So it's done. So you don't have to re-implement everything. So now having NF data defined, we can now define something that's called deep seek. Okay, I'm gonna erase this part. This was just an illustration. And using RNF data, we can define deep seek, which is sort of like the same as seek, except that it does deep evaluation. So deep seek is defined this way. First of all, the stuff that we are deep seeking has to be NF data. NF data. Right? So that's our assumption, that A is actually NF data, because only then we can do deep seek. and we just do R and F acting. Oh, sorry. So it takes A and it takes B and returns B, right? So it takes two expressions and returns the second one. But as a side effect, it forces the evaluation of A. And the implementation is also pretty easy. So DeepSeek acting on some A and B is just equal reduce to normal form A and then sequence it with B, right? That's it. We are just error-netting A and then sequencing. So you see all these primitives, they very nicely combine to produce more elaborate things. Okay? And finally, force. Right? How do we implement force? Also very simple. Force X is evaluate X and DeepSeek it with the same X. So it returns X. Force X is supposed to return X back. But since it calls DeepSeek on X, it will be fully evaluated. Right? So fully evaluate X and then return X. So it's like identity, except that as a side effect, this tongue was fully evaluated.
How does DeepSeek force evaluation?
How does it force evaluation? Well, it sequences it. So it says, you cannot return until you've done this. You have to do RNF of A.
Correct.
Which means reduce to normal form, A. Which means fully evaluate. You fully evaluate A, and then, when it's done, you return B.
Oh.
Okay? B might be already evaluated or not. Doesn't matter.
Why do you need DeepSeek if you already have an RNF? If you already have an RNF?
Well, it's just a helper thing. You don't need it strictly. I mean, you can always write this if you want.
I see.
But this is just a helper function. And we'll see why this is so nice when we talk about strategies, which is right now. Oh, and there's one more extremely useful helper function. Okay, it's called using. Okay, and oh no, that's strategies. Okay, yeah. So let's talk about strategies. So I can erase all of this stuff. You have already memorized it, right?
Yes.
So strategies are actually a way to do all this stuff in a composable way, nicely composable way. Okay? So first of all, what is a strategy? Strategy is a type definition. It's a type strategy of A. So it's just sort of like a type constructor, right? But it's really a synonym for a type that's a function type. It takes A and produces value. So this is a way of just encapsulating this kind of type of function that takes something and produces an eval. Monadic, the eval monad. So example of strategy, for instance, well, return was a strategy, right? Return in the eval monad is a strategy. But more importantly, both rpar and rseek. These two guys are strategies, right? Because they take A and produce eval A. Okay? So we have our two basic strategies already. Now we can combine these basic strategies to produce strategies for evaluating more complex things, right? So this is a strategy for evaluating some data type A. But we might want to define our own strategy of evaluating trees or lists, you know? So this will be a strategy that takes a list and produces eval list, right? So, yeah. And these things are nicely composable, right? The most important thing in programming, composability. They do this. So the example of a strategy that we can come up with is, let's define a strategy for evaluating a pair. That's very simple, right? So let's define a strategy that is called parallel pair. Pair is a strategy of evaluating a pair of A and B. Okay? Which means it's a function that takes a pair of A and B and produces eval of a pair of A and B. So how do we define this? It's pair acting on some AB, right? It's supposed to produce an eval of the pair AB. So we want to produce a monadic value, so we'll start with the do. Okay? And if we want to evaluate them in parallel, then we'll apply rpar to A, and that will be gotten in A prime, and B prime is rpar of B. So this will spark two sparks, right? And it will just evaluate A, and A prime is the evaluated A already, right? And then we have to return this new pair. A prime. That's it. Right? So that's a strategy for evaluating pairs. You give it a pair and it produces, because it's a return, it produces an eval of a pair as we wanted. But it sparks, in the meanwhile, sparks A and B. So that's a nice way of evaluating a pair. And notice that I used these two simple strategies here. rpar and rpar. Well, it's the same strategy for evaluating A and B. Right? But suppose that I want to make it more general so that I can use different strategies for A and B, and I can mix and match these strategies. So in that case, let's define this so-called parametrized strategy. A strategy that takes other strategies as arguments. And this one is called eval pair. And it's also a strategy, but it takes two strategies. Strategy for evaluating A, strategy for evaluating B, and of course a pair AB. So these are the parameters to eval pair. Right? They parameterize how to evaluate A separately and how to evaluate B. And all we do is I can just erase this and put, well, okay, let me know. A prime gets SA acting on A, B prime gets SB acting on B, and then we return A prime, B prime. Okay, so I replace this r-par with SA and SE. And in particular, if I call eval pair with r-par, I'll get back my par pair. Right? So this is more general than this. In particular, we can get this. Now there's this extremely useful helper function that I mentioned. What can I erase? Do I need a buffer? Yeah. So let me erase one pair and define using. So using it says, you know, apply a particular strategy to the evaluation of sum. So it takes this something to be evaluated. It's arbitrary type A. And takes some strategy for evaluating A. And what it returns back is A. Okay? So just evaluate A using this strategy and return it. So it just returns the same thing as the first argument, but the side effect of this, it's evaluated using this strategy. Right? So for instance, an example of using this, and this is the clever thing, because you can then use using in infix notation. And this just makes it really beautiful. It's like say, okay, I want to evaluate a pair of Fibonacci numbers, Fib 35 and Fib 36 as a pair. Okay? But I want to evaluate it in parallel. Right? Oh, so I erased the wrong thing. Using takes two arguments. So this is one argument, and the strategy is par pair. Okay? And now, what it looks like is really, it looks like, okay, this is what I'm doing, really. This is my calculation, Fib 35, Fib 36. Please calculate this. And this, after using, looks like an annotation that says, well, by the way, use this strategy to evaluate it. So it really looks like an annotation. So you can take a sequential program and you can start annotating with using, and you suddenly get parallelism. So that's very nice. Okay. So, do we still have a little time? Maybe I won't talk about the par monad, although it's extremely interesting, but you can just read it in the book. And then there's like many different ways of parallelizing, because there are different strategies for parallelizing. So this is like the most basic one when you use the eval monad, right? There is also a par monad which provides more user control over what gets parallelized and what not, and actually provides a way of between threads to communicate. So you can actually fork a thread. Well, it's not a thread; it's a task, and it's user level tasks. So they are very cheap to fork. So you can really fork small tasks, and you provide a communication between these tasks using these special mutable things called what is it called? MVARs, yeah. So MVARs are communication channels. But remember we said that parallelism in Haskell is deterministic, right? So it will always produce the same result. Now, if we have channels between threads, then suddenly, you know, this is not obviously deterministic. It's like, you know, two threads communicating with a third thread. They put something in one channel, they put something in the other channel, and now you have like which one comes first, which one comes second. It will depend on the timing of these threads and so on. So this would normally introduce non-determinism, right? But determinism is saved in this case because these are like one-shot channels, right? So you can only put once, and when you want to, the other thread wants to get the value, and if the value is not there yet, it will block. So this makes it a network of these puts and gets that are fully deterministic, right? I mean, if you think about it a little bit, you know, you'll figure out that this really has to be deterministic. Using this one-shot channels, yes?
So that's a standard model of parallel computing. It's called
Data flow.
data flow.
Yeah, that's called data flow, yes. Then, so that's data flow programming using the parmonad. Then there is data-driven programming. And there is a library called REPA, which is data-driven programming. So you use like vectors and arrays, you know, and you do these operations and you split them according to data. So you apply the same function to multiple data, right, that are in a list, array, vector. So this is the SIMD model, single instruction, multiple data. And you can run this in parallel. And finally, there is a library for doing parallel programming on GPUs, okay, which are definitely SIMD, right? And it's called Accelerate. And the clever thing, it is implemented as a domain-specific language within Haskell. And what it does is when it's executed, it actually produces code in CUDA, either in CUDA or OpenCL. And it compiles this code on the fly using the CUDA compiler, right, and runs it. So you have like fragments of your program that are written in this domain-specific language, and when they are executed, they produce snippets of code that is compiled for a GPU and run on the GPU. And it comes back, you know, and you do Haskell again, and then you do some more GPU calculations. So all these things are covered in Haskell. I'm not going to talk about them because we are running out of time. Okay? Thank you.
All right.